Okay, we're going to continue on talking gases, and last time we obviously hit a bunch of gas laws. And remember, as we talked about, pretty much if you want an easy way to remember all the gas laws that you need to remember, really that combined gas law is really the good one to remember. Again, that's P1, V1. And if you want to remember it with the moles in there as well, you can. And if you sort of just remember again this version of the combined gas law, which is really just from PV equals nRT, as we talked about, you essentially can just scratch out anything that's not given to you, anything that is held constant, and then you'll pretty much be left with the gas law that you would need to solve that problem. So again, if you had a problem where, again, it said something like constant temperature, doesn't mention anything about moles, as we talked about, you can just basically scratch it off on both sides, and you'll be left with, again, Boyle's law, which is probably the gas law that you want to use. So it's a really good one, this version of the combined gas law, to sort of just remember. And like I said, all you have to do is essentially just scratch out what is not given to you. This is really based off of PV equals nRT and solving for R, which is PV over RT. I'm sorry, not R, but NT. And if you remember that as well, that really this side equals R, you can actually scratch out the whole side and you'll have really sort of a version of the ideal gas law back as well. So again, those are two really good ones to remember. The combined gas law and the ideal gas law are just sort of that one as well. We also talked about stoichiometry that involves gases, and really stoichiometry involves gases. It's like any other stoichiometry problem. You want to balance your equation. You want to convert to moles. You want to double check that it's not a limiting reagent type situation. You want to then do your mole to mole relationship. And then you want to, like normal, kind of take those moles to some other unit. And for the most part, the difference in a gas stoichiometry problem is somewhere along the way you're going to use really the ideal gas law in most cases. I would say most commonly at the end of the problem, much like we did in lab using the ideal gas law a lot of times to solve for volume, which would be nRT over P, is a very common sort of ending as you're asked how much volume of gas you collected. You could also use it as well at step number 2. So instead of using grams to moles or anything like that, you could actually use the ideal gas law and solve for N, which would be PV over RT, and kind of figure out the moles of the gas as well. So those are the two common areas where usually you got to insert sort of the ideal gas law. And I would say probably in a lot of cases, the last step there is usually where you kind of do it. But occasionally the second step, you also do it as well. And again, just to kind of get moles as you go through there. Any questions on that stuff there? All right. So continuing on here, the next one we're going to talk about is, in terms of pressure, is Dalton's law of partial pressures. And the idea of partial pressures is that the pressures of individual gases within a mixture of a gas will basically add up to the total pressure. So if you have, for example, in a container, just one type of sort of gas molecule flying around like A, the total pressure of that container is going to pretty much be all about the pressure of A that's bouncing around in there. Now, if you had a mixture of gases, say in a container, like you had A in there and B gas and C gas, all flying around, now each of those gases are going to contribute to the overall pressure that's happening in there. And now in this case, the total pressure will equal the partial pressure of A plus the partial pressure of B plus the partial pressure of C in this case. These are sometimes referred to, as I just mentioned, as partial pressures because they each contribute to the overall pressure of the mixture of gases. So one of the things when we talk about, for example, the ideal gas law and gases behaving ideally, one of the main sort of factors that make something an ideal gas is under ideal conditions, it doesn't really matter how many gas molecules you have together. They pretty much will not interact with one another. So under an ideal conditions, you could have all three of those gas molecules on the right there, A, B, and C, in that same container. But under ideal conditions, we could actually assume that they're in there by themselves. There'll be kind of no interaction between the different gas molecules. And what that allows us to do is solve problems like this and figure out partial pressures. How do we figure out partial pressures? Well, for the most part, it is our friend PV equals nRT. And we solve for pressure is probably the most common way that we solve for partial pressures. It's just really using the ideal gas law. Now, bless you, when you do have a mixture of gases, like we do over here, a couple of things are really good for everybody in that mixture. Since they're all in the same container, they all will have the same volume. So pretty much all those gas molecules there on the right will have the same volume because they're in the same container. And most likely that container is sitting in the same room, which means the temperature is going to be the same for all gases in the container. R is obviously a constant, which is our gas constant. So really the only thing that typically changes when you need to do like a partial pressure calculation is the moles. And the moles usually are different for each gas. So basically what you would do, for example, here, if you wanted to figure out the partial pressures of A, B, and C is, like I said, just use the ideal gas law for each of those gases separately. And again, under ideal conditions, none of those gases will have any effect on the other gases in there. And you can almost think of them as being in the container by themselves. And you basically just would do three separate ideal gas law calculations. And then to get the total pressure, all you would do is add them together. So sometimes people get really nervous about these type of calculations. They think it's like super hard, but it's really just the ideal gas law for each gas separately, and then you can kind of add them together to get the total pressure. Any questions on that there? And that's what we just talked about here. Obviously, on the left there, just the red gas molecules are going to exert the pressure. Green in the middle. Obviously, both are going to exert there on the right-hand side. Now, also a reminder that for sure, when we use the ideal gas law, as we talked about last time, it is the most restricted in terms of units. So remember that when you go into the ideal gas law, your pressure always has to be in atmospheres, your volume always has to be in liters, N is moles, which obviously should be moles, and T is Kelvin. And R, again, is a value that you always have available to you. And once again, as I mentioned last time, very commonly they never kind of mention R or anything like that in a problem. Just kind of assume that you again know it. So that's another very important thing to be careful of when you're using the ideal gas law. Again, is to make sure everybody's in the correct units when they go in there. That's sort of a 100% rule there. Everybody's got to be in those units. And once again, the reason they all have to be in those units is actually the units associated with the gas constant. Otherwise, everything will not cancel out correctly. So you have to have everybody in those proper units. All right, so why don't we try one here? You have 5 grams of helium and 5 grams of neon are in a 2.5 liter container at 27 degrees Celsius. What is the partial pressure of each gas and what is the total pressure here? Helium is 4.003, I believe. And what was the other one? Neon, I think 2018, I hope. All right, so take a few moments. We're looking for 3 answers here, 2 partial pressures, and what the total pressure will be at the end. All right, so let's take a look. Again, in this situation, we basically got a container and we got helium floating around and we got some neon floating around as well. And we're looking for the partial pressures of each of these. So if we look through the information, we obviously have grams of each, which we can get moles of. We do have obviously a volume of 2.50 liters. We do have a temperature of 27 degrees Celsius. And again, we can think about our PV equals nRT. We are looking for pressure. We do have a volume. We do have a temperature. We always have R, which again is 0.08206 liters atmosphere Kelvin mole. So that means really we're missing moles, and we do need to sort of calculate moles from the grams. So let us do that first. So we'll do our 5 grams of helium. We'll use the molar mass there from the periodic table to convert it into moles. That's going to give us 4.003 grams per mole of helium. And that's going to get us here, looks like 5 divided by 4.003, about 1.24, I think, moles. 1.24 moles. We'll do the same thing for neon, which is also 5 grams. We'll use the molar mass there for neon, which I think is 2018. And we're going to take 5 divided by 2018. And that's going to get us 0.2478 moles. And just to make sure I hit the right number there on the first one, I think I put an extra 3 in there. Pretty close there. 1.249 we'll go with there. There we go. All right, now that we have moles, we do need to make sure everybody's in the right units. So our volume's in liters, so that's good. Our temperature, like normal, is not in Kelvin, so we do need to add our 273.15. That's going to give us a temperature there of 300.15 Kelvin. Now we're essentially good to go. And again, as I mentioned, we're pretty much just going to do the ideal gas law for each one separately. So solving for pressure, dividing by volume to the other side, nRT over V. We'll do this for helium here. And we'll put in our moles of helium, 1.249, our 0.08206, our 300.15, all divided by our volume here, which is 2.50 liters. The moles here will cancel, the Kelvin will cancel, the liters will cancel, and it's going to leave us just atmospheres left over. And if we do that here, we're going to end up with divided by 2.5. We'll end up with about 12.3 atmospheres. This is what is referred to as the partial pressure of helium in this case. Any questions so far on that calculation? Pretty much we're going to tee it up here and do the exact same calculation for neon. Once again, because they are in the same container, the temperature for both is going to be the same and the volume is going to be the same because they're sitting in the same container. So once again, it's really just the moles here that are different. And again, kind of putting it into our equation, we'll use 0.2478 moles. We'll use our gas constant. We will use our same temperature because they're in the same container, and our same volume as well for the same reason. Just like previously there, our Kelvin and moles are going to cancel, our liters are going to cancel. Once again, leaving us just atmospheres. Going to get us 0.2478 times 0.08206 times 300.15 divided by 2.5. Going to give us a 2.44 atmospheres. That again would be the partial pressure of neon. Any questions on that one there? Now, to find the total pressure, I pretty much should do what with both of those numbers? I should just add them. Yeah. So our total pressure going to be the partial pressure of neon plus the partial pressure of helium. which means we're just going to add those together. If I could write the right number, 12.3 atmospheres plus 2.44 atmospheres. And that's going to end up being about 14.7 atmospheres of total pressure in this case. Yeah. Any questions on any of that? Yeah, pretty much. You got like 400 gases. You just kind of repeat this process. And again, the temperature and the volume would all be the same because they're all in the same container. So really the only difference you need to find for each gas is typically the moles, basically the difference between those. Yeah. Other questions? As we see here, between helium and neon, which one is actually contributing more pressure? It is neon, yeah, much more pressure. The reason for that is actually the molar mass difference. Helium is a much lighter gas, which means it will travel a lot faster. It has a faster, what's known as root mean square velocity. It's moving around a much faster. So because it's flying around much faster, it's causing more collisions and contributing more to the pressure than the heavier moving neon, which is traveling slower, has a slower velocity and causing less collisions in comparison. So the smaller the gas molecule in terms of molar mass, the faster it will be flying around and will probably contribute in a mixture of gases under the same temperature conditions. It will contribute probably more to the pressure than some other gas. Any questions on that there? Yeah, so 100% safe bet if it's anything to do with the gas law, gotta go Kelvin, doesn't matter. Again, also, like I mentioned last time, which sometimes tricks people on questions, which is sometimes they are given, or you are given like the temperature in Celsius, and they want like maybe another temperature in Celsius. So people think, well, they gave it to me in Celsius and I'll give the answer in Celsius. I can just kind of leave it in Celsius. But 100% in all gas laws, it got to go into Kelvin, no matter what it is. So in that situation, you have to convert to Kelvin, go into the gas law, and then convert from Kelvin back to Celsius at the end of it. So like when we have one of those ones that have like two temperatures and V over T and V over T type things. Other questions? Yeah, so that should almost be like automatic, the converting to Kelvin. It's like you see a temperature in a gas one, just roll with it. We're not going to worry about this here, so we're going to skip over it, I think. Another type of sort of partial pressure situation that occurs is something that occurred like in the experiment that we did on Monday. It also occurs in this experiment that you no longer do in lab. This was our other gas experiment we used to do. Uh, And for example, here we have some potassium chlorate. And if you heat up the potassium chlorate, it will generate basically, it will break apart into a little potassium chloride and will generate some oxygen gas in this particular case. And what's going to happen in this case is as the oxygen gas is generated, it's got nowhere to go, so it's going to find the tube, and the tube's going to come all the way down here. This tube is in a big old jar of water, basically. Kind of similar to your tube that was filled pretty much with water, right, when you did your reaction. And pretty much as the oxygen gas bubbles in here, the water goes out, and we are displaced here in an empty sort of region in our collection tube, our container, just like you had in your tube on Monday. And we will get our oxygen gas in here, but because of the way that we're collecting this gas in water, we will get sort of a byproduct, as we talked about on Monday, of water vapor. Yeah, so we'll get some water vapor as sort of a byproduct of really just how we're collecting the gas. So in this particular situation, we are not really interested in the water. We're actually only interested in the oxygen gas, which is the gas of interest. So this creates sort of a partial pressure situation where the total pressure in this case would equal the partial pressure of the oxygen gas plus the partial pressure of water, which is known as the vapor pressure of water. In lab, that was the chart that was stuck there on the whiteboard that you went up and looked at it. And that is typically where you find the vapor pressure of water, just like you did in the experiment. You find a chart there based on the temperature, and you look up the vapor pressure of water. So this is really a mixture of two gases, and in this particular case, we're not really interested, like I said, in the water. So to find the partial pressure of oxygen, we basically take the total pressure minus the vapor pressure of water. And the total pressure, for example, when you're doing an experiment like you did it on Monday, is like the barometer readings, the atmospheric pressure. In book type problems, they typically will give you like the total pressure or the atmospheric pressure. They'll kind of mention it in a problem. And it's basically just a subtraction here. The only real thing you have to worry about on this one is just to make sure they're both in the same unit. So the pressure of vapor pressure of water and the total pressure just needs to be in the same units for you to subtract them, and you can do that. So in general, if you have a mixture of gases as a result of collecting your gas over water, the partial pressure of the gas is usually the total pressure minus the vapor pressure of water, which again is something that you look up. How do you know this is the situation? Usually in sort of book problems, there's a couple of things that are usually maybe mentioned in words that sort of illustrate that it is the situation happening. Oftentimes they will say what I just said, which is you collected a gas over water. Or sometimes they'll say you collected a gas saturated with water vapor. So those are sometimes words that they'll use in these problems to indicate that you collected the water in this or the gas in this fashion, and you have to sort of correct for the vapor pressure of water. Any questions on that there? Obviously, my thing here is not balanced, so we can balance it, I suppose. There, three, three, maybe a three there as well. Not three, that's a two. Two there, two and two, and a three there. There you go. All right. Here is again a table from your book, and again you can see basically just like it was on the sort of whiteboard there. You're just going to kind of look it up usually by temperature. And you do want to, like I said, be careful of whatever table you look it up just to make sure everybody's in the same units. Otherwise, it may require some type of conversion. So, for example, if your total pressure is an atmosphere and you look this up in torr, you can ask converted to torr or atmosphere, one of the two values. All right, so why don't you try one here? A sample of oxygen gas is saturated with water vapor at 30 degrees. The total pressure is 753 torr. What is the vapor pressure of water at the vapor pressure of water at 30 degrees is 31.824. What is the partial pressure of oxygen in atmospheres? Okay, so let's take a look at this. So as I mentioned before, this is kind of the key word here in this problem. A lot of times you'll see this saturated with water vapor. So again, that basically is an indication that we're collecting this gas over water, and we do have sort of this situation as we just talked about that the partial pressure of your gas is going to be really the total pressure minus the vapor pressure of water. In this particular problem, they were nice enough to sort of give you the vapor pressure of water. I will say that probably on problems and stuff like that, sometimes you do have to refer to the table and kind of look it up yourself. So we do have this guy. We do have the total pressure here. And in this particular case, both the total pressure and the vapor pressure of water are both in the same units. So here, the partial pressure of oxygen, which is the gas we're interested in, would be our 753 torr minus our 31.824 torr. And that means we will end up with 721 point, we'll call it 2. In this case here, torr. And maybe we'll round the whole number since, it's kind of a chemistry class, I suppose. There we go. And based off that number. Now, we are looking for it in atmospheres. And as we talked about, 1 atmosphere, right, important conversion is 760 torr and also 760 millimeters of mercury. So to convert this into torr, or sorry, atmospheres, We're going to divide by the 760, and that's going to give us our atmospheres in this case. And 0.949, we'll call it atmospheres. So this type of sort of partial pressure problem really is just like a correction value or sort of a correction, and oftentimes sort of pops up in a situation where you're collecting gas in that sort of manner by really displacing the water and collecting the gas in its place. Any questions on that? Now, remember as well, you can also have sort of a partial pressure problem, which, maybe they do give you. Maybe they give you the partial pressure of A and a partial pressure of B is given to you, and you're looking for the partial pressure of C. And maybe they also give you the total pressure as well. So, if you had a problem like that, once again, the total pressure would equal the partial pressure of A plus the partial pressure of B plus the partial pressure of C. And in that situation, if you were given pretty much all three of these, it really is just sort of a subtraction sort of problem. You just got to subtract each of those ones you're given from the total pressure, and you would then know, obviously, the partial pressure of C. So again, that's a variation on this type of problem here, where maybe you're looking for a partial pressure and they give you the others and the total pressure. Any questions on partial pressures here? Yeah. What's that? Up 60 of torr and equals millimeters of mercury? mmHg. Yeah. Other questions? Okay. All right. Then last thing we're going to talk about here in terms of gases is the kinetic molecular theory of gases. And we sort of covered some of this as we went through the different gas laws. But these are the main parts of what's known as the kinetic molecular theory of gases. Gases, as we've been talking about, consist of these tiny particles, atoms, or molecules. These particles and molecules are small compared to sort of the distances between them, that their volume and size of the individual particles are considered to be negligible. And that is one of the main things that makes something an ideal gas. So when we talk about an ideal gas, hence the ideal gas law, that is one of the things that we sort of think about is we are not really interested in an ideal situation, the volume of the gas itself. We're more interested in really the volume of the container it is in. The idea behind that, if you think about a lot of the problems we come across, they do talk really more about the volume of the container rather than the volume of the gas. So it's kind of like if you have that trash can over there and you put like a little small, marble in it, the volume of that marble compared to the volume of the gas of the trash can over there is relatively negligible compared to the big giant volume of everybody flying around in there. And in an ideal situation, that is sort of what we assume. We're not really interested in the little marbles volume. It's more the trash can where it's kind of flying around. In a non-ideal situation, or what is sometimes referred to as a real gas, which we don't talk about in this class and you'll talk about in the next class, you do have to, in certain situations, take that into account. And it's a situation where perhaps you threw maybe a basketball into that trash can. Now the volume of the basketball is pretty relevant compared to the volume of the trash can in that particular situation. The particles are in constant motion as they're colliding. Those collisions is what exerts the pressure that we associate with gases. Number 4 here is really the second reason that we sort of make something an ideal gas. Under ideal situations, we assume that particles neither are attracted to one another or repel one another. And that is sort of like your second sort of reason of something that makes something an ideal gas. That is also the reason why in the problems we just did, where we had mixtures of gases all in the same container, we're able to sort of assume in an ideal situation that they're just kind of like in there by themselves, and we can do the calculations individually for them as there's no attraction or repulsion. If there was attraction forces or repulsion forces between molecules, that would affect something like the pressure, right? Because If we had a gas molecule in an ideal situation heading towards a wall, there's nothing that's going to stop it from hitting the wall, basically. If you had sort of a gas in a non-ideal situation that's maybe attracted to this molecule, that's going to kind of slow him down as he heads towards the wall, as he's attracted to somebody behind him, and that's going to have an effect, say, on the pressure of that container. And again, in a real gas situation, non-ideal situation, you do have to take that into account. The good news on that is real gas situations or non-ideal gas situations usually happen at really, really large pressures and very small volumes. And if you just think about the relationship between pressure and volume is when we have really large pressures, the volume's super small, which means now all the gas molecules are really near each other. You have to take into account how they interact with one another because they're basically on top of each other. And same thing with very small temperatures as well. They're not moving as fast, and that means that they're going to be near each other for a much longer period of time, and they are going to sort of interact with each other. But the good news is we don't deal with that here, so you'll see it in the next class. And what that ends up doing, as you will see in the next class, is it turns the ideal gas law into a very scary looking gas law, which is known as the van der Waals equation, which is like the ideal gas law with a bunch of correction values and stuff on it. The average kinetic energy of a gas molecule is directly proportional to its temperature in Kelvin. So as the temperature increases, we do expect the gas molecules to fly around faster. And as the temperature decreases, we expect it to slow down. So you should be familiar with the sort of points of the kinetic molecular theory. A couple of relationships that we talked about. Again, that's important. The temperature is measured motion of gas. Again, we're going to have faster moving gas molecules at higher temperatures, can cause more collisions and can have an effect on the pressure. And lower ones are going to move much slower, going to probably have less collisions. In a rigid container where the volume doesn't move, obviously, as we increase the temperature, as we talked about in sort of Guy-Lussac's law, we will see an increase in the pressure. And as we decrease the temperature, we will see a decrease in the collisions and a decrease in the pressure. And obviously, if the volume can adjust, that is in Charles' law, as we talked about, how it's able to keep constant pressure, more higher temperature, more collisions, volume gets larger to maintain the proper constant pressure, lower temperature, sort of less collisions, volume drops lower so that we can maintain the same number of collisions and keep a constant pressure. And that is the gas chapter. Any questions on that there? All right, we're going to then go off to chapter 14, is the start of next exam stuff. Yeah, so 13 is the last one. So we're going to talk about liquids and solids, mainly liquids in here, and it's not too long of a chapter, so let's get into it, I think. Water, as we've talked about, a couple important things about water, which is obviously water is normal boiling point is 100 degrees Celsius and normally will freeze at 0 degrees Celsius. So that's normal freezing point as well. One of the unusual sort of properties of water is its density. And it's one of a few substances where its solid state is actually less dense than its liquid state. And as we'll see a little bit in this chapter, one of the reasons is in its sort of solid state, when these water molecules basically come together and bond together with each other, what ends up happening is it creates a lot of open spaces between the different water molecules. And because they're in the solid state, they don't have as much energy to get really close to one another. So they can only get so close to one another. And as they kind of lock into the solid state, it creates a lot of this really open space. And if you think about the density equation from a throwback formula, right? Density is mass divided by volume. So because when they come together, they create a lot of this really open area between all the gas or the water molecules, the volume gets really bloated and this number gets larger. And because that number gets larger there, the density actually gets smaller, right? Because we're divided by a bigger number on the bottom. So the density decreases. And we end up seeing that ice, for example, has a density of 0.917 versus our kind of standard density value for water, which is 1.00 grams per milliliter. So that's a very unusual sort of property, and it is a combination of them not having as much energy and also um, what holds them together, which is hydrogen bonding, which is a really strong sort of attraction force between the water molecules. Now, this is a heating and cooling curve, and as we come down here and go from ice, which is the solid state of water, to liquid water, to obviously steam, which is the gas state, what we see is a couple of transitions. And when we hit here at 0 degrees, which is this normal freezing point and melting point, we also come over here at 100 degrees, which is this normal boiling point. We do see that this graph plateaus at each of those spots. And what that means is, as you hopefully remember, where water, for example, freezes or goes into the liquid state, that all occurs at the same temperature. And at exactly, for example, 0 degrees Celsius, you have basically both phases happening at the same time. So at 0 degrees Celsius, you have some liquid water, you got some ice there, kind of like ice crystals happening. And the same thing happens at 0 degrees. We see this line is flat line, which means the temperature is not changing. And at exactly 100 degrees, you have both liquid water and sort of steam or gas happening at the same time. It's not until you get a little bit above 100 degrees that you fully transition into the gas phase, not until you're a little below 100 degrees that you kind of fully transition into the liquid stage. And the same thing at 0 degrees, not until you get a little bit above 0 degrees that you transition to the liquid stage, or below 0 degrees that you're into the solid stage. Now, when we talk about these transitions, there is actually a certain amount of energy that is required to do nothing more than take a substance from one state to the next. And when we're talking about the transition of going from solid to liquid, or liquid back to solid at the normal freezing point of a substance, that is the heat of fusion. And the heat of fusion is the energy required basically just to do that. Temperature is not going to change. It's basically, for example, taking water at 0 degrees and turning it from water and ice at 0 degrees to liquid water at 0 degrees. So we're not changing the temperature. We're simply just the energy required to change the phase of it. And for water and ice, it's about 6.02 kilojoules per mole, which is roughly 335 joules per gram, give or take a joule. And remember that as we go from solid to liquid, that is an endothermic process. Energy needs to be put in. And when we talked about energy and things that are endothermic, those values are positive energy values. So it would take about positive 335 joules per gram to go from solid to liquid. When we go from liquid back to solid, that is an exothermic process. Energy has to be released, and those are usually negative numbers. So it would actually be negative 335 joules per gram to go in the opposite direction, to go from liquid back to solid. So remember, our negatives and positives with energy also is in play here. Negative is exothermic, releasing energy, and positive energy values are endothermic, absorbing energy. There is also a certain amount of energy required to do the transition of going from liquid to gas, or gas back to liquid. That is what is known as the heat of vaporization. And that is the transition or energy required to do either of these transitions, liquid to gas or gas back to liquid. And that is for water, specifically 40.6 kilojoules per mole. That is roughly 2260 joules per gram, if you want to do joules per gram. And same idea here as we go from liquid to gas, that's an endothermic process. So that is a positive 2260 necessary to do that transition. And as we go from gas back to liquid, that is a negative 2260 to kind of go in that direction. Now, where do these come into play if we look back on that little graph we were just saw there? That is right here. So this transition where the temperature is not changing and we're going from solid to liquid, that is where the heat of fusion would come into play. And right here where we're going from liquid to gas, again, where it's flat line and the temperature is not changing, that is where the heat of vaporization would come into play. By the way, the heat of vaporization is sometimes abbreviated as delta H of vaporization. That is sometimes the symbol that is used to represent that energy value. And for fusion, sometimes it is used as a delta H of fusion. If you remember, delta H is the change in enthalpy that we talked about in that energy chapter, and that is sometimes how that is represented in a sort of a problem and stuff like that. First off, any questions on that there? So let's say, for example, whoa, here. Let's say, for example, that we wanted to do this problem here, which is how much energy is required to change 75 grams of ice at minus 3.5 degrees Celsius to steam at 102 degrees Celsius. Now, we can kind of follow the steps here in this sort of calculation, and it is also going to involve something that we've seen before, which is, I'll come back to this one so I don't mess that graph up here. That is our specific heat. If you remember, Q equals ms delta T, our specific heat equation that we used in that previous chapter. And this is also in play here because when we use this equation, this is when we have something that we have a change in temperature, but it is the same phase. Now, we use that equation, again, we're changing temperature and we're keeping the same phase. We use the heat of fusion or the heat of vaporization when we are changing the phase of something, taking it from solid, liquid, or gas, but keeping the same temperature. So if you were to sort of visually look at this graph and sort of figure out, where should I use certain things, anywhere on this graph, essentially, that you are changing temperature. So on this graph, that's anywhere where the line is pretty much going up or down, depending on which way you're going. Those are all situations where you are changing the temperature, but things are in the same phase. That is when you would use your specific heat equation here along the way. Anywhere where you are, again, as I mentioned, not changing the temperature, line is flattened, but changing the phase, that's going to require a heat of fusion or a heat of vaporization. So when you have a problem like we're going to kind of look at here, you do want to kind of think about where you are maybe on this graph. You can kind of follow along. So let's go through this sort of calculation here and kind of talk about it. All right, so we want to basically figure out how much energy is required to take 75 grams of ice from minus 3.5 degrees Celsius to steam at 102 degrees. So we're essentially starting like right here, and we eventually want to get up all the way over to there is sort of where we want to end. And this is a process that occurs sort of in steps. So the first thing that would happen is we would take our ice at minus 3.5 degrees Celsius and take it to ice at 0 degrees Celsius. That would be like our first step here. So let's take a look at that. So the first step would be ice at minus 3.5 degrees Celsius to ice at 0 degrees Celsius. They are both ice, which means they're both in the solid state, but we are changing the temperature. So this is a same phase, different temperature. This is a situation, if you look at the chart here, we're coming up this line. This is a situation where we're going to use our specific heat equation. So we're going to use Q is equal to ms delta T. And in this case, Q is going to equal our mass, which is 75 grams. We're going to use our specific heat capacity. So this is really important. We all have memorized in our head, right? The specific heat capacity of liquid water is 4.184 joules per gram per degree Celsius, right? This is not liquid water, right? This is ice. So the specific heat capacity for ice is different than the specific heat capacity for liquid water. It's around 2, so we'll call it 2. It's actually 2 joules per gram per degree Celsius. So this is the specific heat capacity for ice. And that's really important when you're doing a problem like this. If you happen to be in a different phase, you want to make sure that you're using the proper sort of specific heat capacity. Now, our final temperature in this case is 0. Our initial temperature is minus 3.5 degrees Celsius. And that's going to give us, for this very first step, an amount of energy of 75 times 2 times basically 3.5. Can give us about 525 joules of energy is needed in this case. Any questions so far? Now, as we climb up this, we are now going to be sitting at 0 degrees Celsius ice. We're going to have to now do a phase transition and take that 0 degrees ice to 0 degrees liquid water. So we're now going to have to kind of do the change in phase from solid to liquid at this point. And if we look at our map here, our diagram, we're now going to cross over right around here. And we're going to do this flat line right here, the second step, which is basically changing the phase of it. Once again, looking at the map here, we are not changing the temperature. We are just changing the phase. And that is where the delta H of fusion, or the heat of fusion, comes into play at this point. So the second step along the way here would be to take it from 0 degrees ice to 0 degrees liquid water. And that is our heat of fusion that is necessary. And I'm going to use the joule number because this is in joules, so that's like 335 joules per gram. So to do this, we simply take the mass of our ice and we times it by the heat of fusion, 335 joules per gram. And that's going to give us the energy again to simply change the phase of the substance, not change the temperature. And we're going to go 75 times 335. And that's going to give us about 25,125 joules of energy is needed to change our ice into our liquid water. Any questions at that point? Because we started at minus 0.35 degrees Celsius. The first transition that we would take it to is we had to take it up to 0 degrees Celsius, which puts us right here on the map, right here. And because now we're at 0 degrees Celsius and this is the normal freezing point or melting point of ice, we now have to do the transition going from 0 degrees ice to 0 degrees liquid water. We're not changing temperature. We simply have to take our ice from solid form to liquid form at the same temperature. And that's what's happening here. It's 0 because in this case it's water, and that's its normal freezing point and melting point in Celsius. Yes, yeah, exactly. So if we were actually doing some other substance other than water, it may have a different kind of freezing point and melting point temperature. But because this is water, it freezes at 0 degrees and boils at 100. Yeah. Other questions? All right, so we've done the transition. So right now we are sitting here on our diagram right here, and we are now sitting at 0 degrees liquid water. The next thing that we could do on this diagram is we got to take it from 0 degrees liquid water all the way up to our boiling point, which is 100 degrees liquid water. That is all liquid water through that red line I just drew. That's all the same phase, but we're changing the temperature. So this is again back to a specific heat type calculation. And this would be our third step. And let's do that calculation. So the third step is now that we've transitioned into liquid water at 0 degrees, we basically got to take it now to its next major transition, which is 100 degrees liquid water. And that's going to get us to the next boiling point, basically. So here we would use our Q's equal to ms delta T. And we will put in our numbers, which again is still 75 grams. But now we're in liquid water. And because we're in liquid water, we can now use our liquid specific heat capacity, which is 4.184 joules per gram per degree Celsius. Final temperature is 100 degrees Celsius. Initial is 0 degrees Celsius. And that's going to give me here 75 times 4.184 times 100, about 31,380 joules of energy to take it from 0 degrees Celsius to 100 degrees Celsius liquid water. So that's how much energy you got to put in there to basically get it to its boiling point. Yeah. At this point, if we take a look at where we're at in our journey here, we're getting close. We're now really at 100 degrees Celsius, which is the normal boiling point for water. So what we're going to have now happen is another phase change. We're going to take it from liquid water at 100 degrees to steam at 100 degrees. So basically going from liquid to gas. And that again is this flat point right here, where we're not changing the temperature, but we are changing the phase. And that's going to be our heat of vaporization that's going to allow us to do that. That's the energy to do that transition of going from liquid to gas. So looking at number 4 here, we're going to go from 100 degrees liquid water to 100 degrees steam, which is gas. And that is the delta H of vaporization. And again, specifically for water, that is 2260 joules per gram. By the way, just like we just talked about a second ago, that if we were not doing water, we would have different melting points and boiling points. If you're not doing water, you will also have different heats of fusion and heats of vaporization. So these numbers are specific, the heat of fusion, the heat of vaporization for water. So if the substance changes, there'll be different values. So we're going to take our 75 grams here. We're going to times it by, again, I'm going to use the joule number, heat of vaporization. And we'll go 2260 times 75. Going to get us about 169,500 joules to transition from liquid to gas. Just taking a moment here and comparing two numbers, which one requires more energy? Which transition requires more energy? The transition between solid and liquid, or the transition between liquid and gas? Yeah, liquid to gas always takes a lot more energy to do. You can even see that on the graph here. It's a much longer line than the one on the bottom. And that is because as you go from solid to liquid, everybody's still relatively close to one another. But as you do that transition of liquid to gas, everybody is now broken apart and flying around in the gas phase, right? So they're much farther away. So it takes a lot more energy to get everybody broken apart. The last step here is we are now sitting pretty much at 100 degrees steam. We want to end up at 102 degrees, and that would be our last step of the way. Here we're both in the same phase, but we're changing temperature, so we're back to our specific heat sort of formula to do this. And maybe I'll do it like right here. Just try to squeeze it in there. Number 5, we're going to go from 100 degrees to 102 degrees steam. And again, we're going to use Q is equal to ms delta T. And in this case, we're going to, actually, I'll flop it on the next page here. So Q is equal to ms delta T to do that. So we have our 75 grams. Once again, though, we are now at steam, which is gas. So you do want to use the specific heat capacity for steam or gas. Oddly, it is about 2 as well, so I'll just use the rounded number. They're both about 2, ice and gas, actually. Joules per gram per degree Celsius. Final temperature 102, initial temperature 100 degrees Celsius. And that's going to get us here 75 times 2 times 2, basically. About 300 joules of energy. And we're now at where we want to be. If I wanted the total pressure, the total energy, what I need to do is add up all the steps, right? So if I want the total amount of energy required to do all of the transitions, it would be the energy of step 1 plus step 2 plus step 3 plus step 4 and step 5. And if we do that, let's just add that up. We're going to take our 300 for step 5, our 169,500 for step 4, our 31,380 for step 3, our 25,125 for step 4, and our 525 for step 1. And that ends up being about 226,830 joules, or if you want kilojoules divided by 1,000, about 226.8 kilojoules of energy is necessary to do that transition. First off, any questions on that? So again, anywhere where you're kind of changing the temperature, same phase, specific heat equation. Anywhere, same temperature, different phases, heat of fusion. By the way, if I did this exact problem and the only difference was I was going in this direction, started as steam and ended at liquid or ice, what would be the only difference? This number would be negative, yeah? Everything would be exothermic, and you would end up with the exact same numerical value, but the number would just be negative along the way in each of these steps. All of these steps are endothermic energy going in because we're melting ice all the way down to steam, and everything would be the same. Any questions on that? All right.